Hello, good morning, good afternoon, good evening. This is Tasien. I'm happy to be here again. Welcome to Mathify Analytics. In today's video, I'm going to break down one beautiful, simple, but yet powerful formula, mathematical formula called Euler's formula. But guys, did you know that these three most famous and mysterious mathematical numbers, E, this E, Euler number, and the imaginary unit number, I, and this pi number, these three numbers can be connected with one simple but yet powerful equation, and that equation is known as the Euler formula, and that equation is written as e power I x equal to cosine of x plus I sine of x. This is the Euler formula, but where does it come from? Where does this formula come from? In today's video, I'm going to break it down step by step. And I hope you are going to enjoy it. You are going to enjoy this video. And if you happen to like the video, remember to click like. Like the video. This simple act of liking our videos, it means a lot for us. Like it and share to your friends. And if it's your first time to be on this channel, please don't forget to subscribe so that you will get more videos like this in the future. So let's go deeper in our proof. We are going to see where this formula come from. But before I start proving this and showing this formula, let's think about this. What does it mean? What does it mean to raise a number to exponentiate a number? Let's say e power x when x belong to r. What does it mean? Normally, exponentiating a number like this, it means that we are stretching that number along the line of real numbers. Just stretching it along the line of real numbers. But what if we introduce the imaginary power in this number? What does it mean when we introduce this imaginary power, e power I x? It will not be any more stretching the number on the real line. It will become a rotation. We will be rotating these numbers in the complex plane. We will have something that looks like this. If I try to show it here, we have something that looks like this. Yeah, let me take this image a little bit up here. Yes, if we have this, let's say this e power I phi, we are trying to rotate. We will be rotating because this phi we can vary. This is an angle. I like using phi or x or theta, whatever, but what we have to know is that this is an angle, and we can rotate in the set of in the complex plane, and this is the real axis, and this will be imaginary axis. But if you remember, you remember in trigonometry, when we have a point here, this point will be characterized by its value down here. This length, let me call it A, and this length here, and let me call it B. Yes. In trigonometry, this point here, it's the point that characterized by cosine phi and this sine phi, this point. Yeah, and it means that this A is equal to cosine phi, and this B is equal to sine phi, like this. Yes. And on unit cycle, trigonometric cycle, this radius A, this A is always equal to 1. It's equal to 1 when we are on unit trigonometric cycle. So if it is equal to 1, then this complex number, or this complex number, let me call it z. If I go to complex plane z, this z will be equal to a, of course, this distance, then plus I times b. The imaginary part is b. We can write I times b, or we can write just a plus b, bi. And if we go ahead and replace a by cosine phi and b by sine phi, then z will be equal to cosine phi plus I times b. B is sine phi. And if we replace z by this value, then we will have a e power I phi equal to cosine of phi plus I sine of phi, and this a is equal to 1. So we have e power I phi equal to cosine of phi and plus I sine phi. So this is the geometric representation of our Euler formula, and in geometry we can represent it like this. But we can prove it. We can make a very more comprehensible way to prove this mathematically or algebraically. Is to use the Taylor series. Do you remember the Taylor series? We can prove this Euler formula using Taylor series. And if you are interested, keep watching this video, because I'm going to use the Taylor series to prove this relation. Yeah. Yes, I'm going to start by expanding. We are going to first expand this function f of x equal to e power x. And we are expanding it using the Maclaurin series, which is a version of Taylor series. Do you remember the Taylor series? When we have a function f of x, the Taylor series is writing this function in this form: summation n from 0 up to infinity of n derivative of this function in a given point a over n factorial times x minus a power n. And for Maclaurin, we take a to be equal to 0, and I'm going to use this case. Yes. So let's expand our function f of x equal to e power x using Maclaurin series. The first thing that we have to do, we first compute f of 0. And f of 0 will be equal to e power 0, which is equal to 1. And next we compute the first derivative in 0. And the derivative, yesterday in our video, we proved that the derivative of e power x is itself. If you didn't watch that video, I recommend you to go and watch it, and I'm pinning the link in the comment section. The derivative of exponential function is itself. E power x derivative equal to e power x. So f derivative in 0 will be equal to e power 0, which is equal to 1. And next, f second derivative also will be equal to e power x, then in 0 e power 0, which is equal to 1, and so on. So that if we use this, we will get the Maclaurin expansion or series of our function f of x e power x will be equal to this 1 over 0 factorial times x minus 0 power 0 and plus this number 1 over 1 factorial and times x minus 0 power 1 and plus this number here 1 over 2 factorial and times x minus 0 power 2 plus and so on up to infinity, so that we will get e power x equal to this will be equal to 1. So then 1 and plus 1 over 1 factorial, that's 1, and x power 1, that is x, and plus 1 over 2 factorial, and then x squared over 2 factorial, and plus I can continue up to x power 3 over 3 factorial plus x power 4 over 4 factorial plus x power 5 over 5 factorial plus and so on. This is the Maclaurin expansion of the exponential function. So if we use this Maclaurin exponential function to our function that we have in the Euler formula here, I mean this. Now we are going to expand this one. If we expand it using this Maclaurin expansion, what are we going to get? We are going to get e power I x to be equal to, we are going to replace in this relation where we have x, this x is x, we are going to replace it by ix. Yes. So what are we going to get? We will get e power ix to be equal to 1 plus ix and plus ix squared over 2 factorial and plus ix power 3 over 3 factorial and plus ix power 4 over 4 factorial and plus ix power 5 over 5 factorial plus and so on. Yes. So now, do you remember that when we have I squared, this is equal to minus 1? We are going to use this in expanding this sum. So we will get e power ix to be equal to 1 plus ix. Then in here we have I squared times x squared, and I squared is equal to minus 1. So we will get minus 1 minus x squared over 2 factorial. And in this term here, we have I power 3 times x power 3. And I power 3 is like I squared times I. and I squared is equal to minus 1. So then minus, we will have minus 1 times I, minus I times x power 3. So we have minus I x power 3 over 3 factorial, and then in here we have I power 4 times x power 4, and I power 4 is minus 1 times minus 1, then 1, we get plus, then plus x power 4 over 4 factorial, and in here we will have plus I, then plus I x power 5 over 5 factorial plus, and so on. What are we going to do now? Now we are going to put the imaginary part. We are going to separate the real part and the imaginary part. We are going to separate the real part and the imaginary part, and if we separate those two parts, we will have the real part to be, we have one here, but in here, let me use another color. Here. In here we have I, and in here also we have I. Yes, and in this term also we have I. And the remaining ones will be the real part, and this with I will be the imaginary parts. So we will have the real part to be 1 minus x squared over 2 factorial and plus x power 4 over 4 factorial plus and so on up to infinity. And the imaginary part will be, let me use this plus, and then the imaginary part will be, we start from here, we have ix, we have x, and we have ix power 3, then plus x power 3 over 3 factorial. Now, is it plus? It's minus. I have a minus sign. Minus, not plus. Minus x power 3 over 3 factorial and plus x power 5 over 5 factorial plus and so on. Plus and so on. Plus and so on. Then times I. This is the imaginary part, and this is the real part. Now, what do we have in the imaginary part and what do we have in the real part? Do you know any function when we expand it? Do you know any function when we expand it, we get this real part? And do you know another function when we expand it, we get exactly this imaginary part? Yes, those functions, one is cosine of x and the other one is sine of x. Maybe I can also show you why if you want to, but if you don't want to, you can just write that we have cosine x and sine x. But let me show it to you why. When we have a function f of x, let me call it gx equal to cosine of x, and if we expand it also, we will first compute g of 0. G of 0 will be cosine of 0, and cosine of 0 is equal to 1. And g derivative of x will be equal to cosine derivative of x, cosine derivative, which is equal to minus sine x. And then this implies that g derivative in 0 will be equal to minus sine of 0, and sine of 0 is equal to 0. And then the second derivative, the second derivative of x will be equal to derivative of this one, derivative of minus sine x. And if we differentiate this one, we will get minus cosine x. Then g second derivative in 0 will be equal to minus cosine of x, which is equal to minus 1. And the third derivative, the third derivative of x will be equal to the derivative of this one, minus cosine x derivative equal to this is sine x, which implies that g third derivative of 0 will be equal to sine of 0, which is equal to 0. And the fourth derivative, g fourth derivative of x will be equal to the derivative of this. It's a sine of x derivative, which is equal to cosine of x, which implies that the fourth derivative in 0 will be equal to cosine of 0, which is equal to 1. And using this to expand cosine of x, we will get that cosine of x is equal to what? It will be equal to this number 1. It's a 1 over 0 factorial times x minus 0 power 0, and then plus 0, we have 0 here, plus 0 over 1 factorial times x minus 0 power 1, and minus this one, minus 1 over 2 factorial times x minus 0 power 2, and the third one is 0, I don't need it, even this one. Then the fourth one will be plus 1 over 4 factorial times x minus 0 power 4. So that we will have cosine of x equal to, this is 1, so equal to 1, and this is 0, then minus x squared over 2 factorial and plus x power 4 over 4 factorial plus, or not plus, minus, the next one will be minus, may not mix things, minus, and so on. So you can see that this relation, this one is exactly this real part. It's exactly this real part. In a similar way, you can go ahead and expand sine x, and if we expand sine x, you will end up by getting this imaginary part. This is equal to sine x, and this real part is equal to cosine x. And finally, we will have our Euler relation, our Euler formula, which is e power I x equal to cosine x plus I sine x. So that's where the relation came from. Yeah. And then now let's connect together our three numbers. Do you remember where I start from? I said that we can connect our beautiful numbers, the Euler number and the unit number I and the pi together using this Euler formula. But how? This is the bonus that I'm going to give you. The bonus Let me use another color for this bonus. Or I can use, of course, black or red or something. Okay, let's take this green color. Yeah. From this Euler formula, we have e power I x. What if we take x to be equal to pi? If x is equal to pi, we have e power I pi equal to cosine of x, and x is pi, then cosine of pi plus I sine of x is pi, then sine of pi. Do you see? Then we have that e power I pi is equal to cosine of pi is equal to what? Cosine of pi is equal to minus 1. Then plus I sine of pi. I sine of pi is equal to 0. Then we will have e power I pi equal to minus 1. Or simply you can write e power I pi plus 1 equal to 0. And this function is very useful. Yeah. Is this the function? It's equation. This equation is very powerful. That's the relationship between this Euler number, the imaginary unit number, and pi. So e power I pi plus 1 equal 1. That's it. That was it for today, and I hope you have gained something from this video. And if you have gained something, please don't forget to click like the video and share the video to your friends. If it's your first to be here, or if you have not yet subscribed and you wish to see more videos like this in the future, subscribe to our channel. Click subscribe and turn on the notification bell so that you will get notified anytime we upload a new video. Thank you for watching. Bye.